Using the parent function f of x, graph g of x using the new function rule g of x equals 1/2 times f of the quantity x plus 1 minus 2. Looking at the graph of f of x, we may recognize this as the graph of f of x equals the absolute value of x, which indicates f of the quantity x plus 1 equals the absolute value of the quantity x plus 1, and we could write g of x as g of x equals 1/2 times the absolute value of the quantity x plus 1 minus 2. Notice in this form, we have c equals -1 and d equals -2. If we want h equals -1 and k equals -2, this would be the vertex of the absolute value function g of x, and then from there we could find additional points using a table. However, the point of this question is to use function transformations to graph g of x, and therefore we'll take this approach for the question. Recall, if g of x is a transformation of f of x, we can write g of x in the form of g of x equals a times f of the product of b and the quantity x minus c plus d, where, for review, the value of a indicates a vertical stretch or compression, the value of b indicates a horizontal stretch or compression, the value of c indicates a horizontal shift, left or right, and the value of d indicates a vertical shift, up or down. Looking at the rule for g of x, notice a equals 1/2, b, the coefficient of x, is 1, c is -1 because x minus -1 simplifies to x plus 1, and d equals -2. A equals 1/2 indicates a vertical compression by a factor of 1/2. B equals 1 indicates there is no horizontal stretch or compression, and therefore b does not affect the graph. C equals -1 indicates a shift left 1 unit, and d equals -2 indicates a vertical shift down 2 units. To perform the transformation on f of x, we'll work our way from the inside out. Starting inside the parentheses, we have the x plus 1, which indicates c equals -1. Again, this indicates a shift left 1 unit. Before we perform the shift left 1 unit, though, let's find 3 key points on the graph of f of x. For example, we'll use the vertex 0, 0, and then because a equals 1/2, we'll select 2 other points where the function value or y value is a multiple of 2. Let's use 4, 4, and -4, 4. Of course, we can also use 2, 2 and -2, 2. And now to shift the graph left 1 unit, we subtract 1 from each of the x values. Starting at the vertex 0 minus 1 is -1. The vertex is now -1, 0. For the point on the left, -4 minus 1 is -5, giving us -5, 4. And for the point on the right, 4 minus 1 is 3, giving us 3, 4. We graph the new function. This is the function after being shifted left 1 unit. And again, working our way from inside out, we now have a equals 1/2, which is a vertical compression by a factor of 1/2, which affects the y values. We now multiply each y value by 1/2. Starting at the vertex, 0 times 1/2 is still 0. The vertex is still -1, 0. For the 2 remaining points, 4 times 1/2 is 2, giving us -5, 2, and 3, 2. And now we graph the function. This is the graph after being shifted left 1 unit and a vertical compression by a factor of 1/2. And then finally we have the -2 on the end, which indicates d equals -2. This indicates a vertical shift down 2 units. We now subtract 2 from each of the y values. For the vertex, 0 minus 2 is -2. The vertex is now -1, -2. Subtracting 2 from the y value of the remaining 2 points, 2 minus 2 is 0, giving us -5, 0, and 3, 0. This is the graph of g of x, which, starting with the graph of f of x, is a shift left 1 unit, a vertical compression by a factor of 1/2, and a shift down 2 units. I hope you found this helpful.